Attention is the core building block for generative AI. It allows us to capture contextual information within a sequence. But standard attention mechanisms still suffer from quadratic compute and linear memory constraints. Can we overcome these limitations? Let's first review how standard attention works. The input to an attention layer is a sequence of embedding vectors, one for each token. We use query and key matrices WQ and WK to project each d-dimensional embedding vector into query and key vectors. Each of these vectors have a lower dimensionality, say dk. For instance, each query and key vector may have 128 dimensions. We compute the relevance between tokens using the dot product of their query and key vectors. As the model generates token one at a time in an autoregressive manner, we consider only how each token relates to all preceding tokens in the sequence. We then apply a Softmax function to transform these raw dot product scores into a normalized probability distribution. These normalized values are referred as attention scores. The attention scores specify how much each token should influence the update of a particular token's embedding. For each token, we obtain its value vector by projecting the embedding through a value matrix. This extracts the contextual information that could be retrieved and transferred to other tokens. Next, we aggregate the value vectors into a single representation for each token by computing a weighted sum, where the weights are given by the attention scores. But the value vectors typically have much lower dimensionality than the original embedding dimension d. Therefore, we use an output matrix WO to convert the output vector back to the same dimensionality of the token embedding. We then add these residual embeddings to update the original token embeddings. This self-attention mechanism enables the model to incorporate contextual information into each embedding, ensuring the refined embeddings capture relevant details from the entire sequence. But explicitly writing out individual vectors can quickly get out of hand. Luckily, we can represent the computation in a simple and compact matrix form. We denote the stack of query vectors as Q and a stack of key vectors as K. This lets us concisely represent all pairwise dot products as one single matrix multiplication, QK transpose. We add a masking matrix M to ensure that the tokens only attend to itself and the tokens that came before it. With the attention weights, we express the output matrix O in matrix form. In short, we can express the entire attention mechanism as a function that takes Q, K, V as inputs. To obtain the residual embedding, we multiply the output matrix O by the output projection matrix WO. This phase is called the prefilling stage, during which the model processes the input prompt or the given context. But things become interesting when we begin to generate the output response. Let's say X6 is the first token in the output response. Our goal now is to compute the attention output O6 using the context provided by the preceding tokens. Similar to the prefilling stage, we extract the query key vectors using the corresponding matrices. With these vectors, we compute the attention scores by taking the dot product and normalizing them with a softmax function. We can then produce the attention output O6 by computing the weighted sum of the value vectors. During this process, the key and value vectors from the previous tokens do not change at all. This is true across multiple attention heads in all attention layers. Recalculating the key and value vectors for each token is wasteful. A simple solution is to store the key and value vectors from the previous tokens in memory and reuse them when needed. This technique is known as key value caching, or KV caching for short. We don't need to cache the previous query vectors because in autoregressive generations, all these entries are masked out and have no effect on the attention output. The KV caching helps speed up the decoding process. But the memory requirements grow linearly with the sequence length. This limits the applicability for problems that require long context windows. In the previous video, we discussed several improvements that aim to address the limitation of linear memory growth, including group query attention, multi-head latent attention, or deep-sea sparse attention. While these improvements offer some relief, they do not fully resolve the linear memory growth problem in standard softmax attention. This is where linear attention comes in. Linear attention is simply softmax attention, but without the softmax function. Let's see how it works. Without the softmax function, the attention scores are simply the dot products between the query and key vectors. We can compute the output vectors by summing the value vectors weighted by the attention scores. For example, the first output vector, O1, is the value vector V1 weighted by the dot product between the query vector Q1 and the key vector K1. The second output vector, O2, is the weighted sum of the value vectors V1 and V2. Similarly, for each token, we compute the output vector as a sum over the value vectors of all previous tokens, where each value vector is weighted by the dot product between the current query and the corresponding key vector. Concisely, we express the output vector OT as this equation. This is the linear attention mechanism. Compared to the standard softmax attention, linear attention removes the nonlinear softmax function for normalizing the attention scores. Let's take a look at the equation. Each term involves three vectors: query vector Qt, key vector Kj, and value vector Vj. Here, the query vector Qt remains the same throughout the summations over index j. Due to the linearity of dot product, we can factor out the query vector Qt from the summation. Now let's give this summation a name as state matrix St. The state matrix St is formed by summing over rank 1 outer products of the key and value vectors. It has dimension dk by dv. Usually the dimension dv is said to be the same as the dimension dk, typically 128. We refer to the state matrix St as the matrix value's hidden state. Now let's move the key and value vectors at t's positions outside the summation. We recognize that this term that sums over j from 1 to t-1 is just the state matrix St-1. Therefore, we can express the state matrix St using a recurrence relation. This recurrent relation offers us a fresh perspective on how linear attention works. At a high level, linear attention takes a sequence of query, key, and value vectors and produce a sequence of output vectors. Let's start with the first token. We initialize the hidden state S0 as a matrix where all the entries are zeros. To update the state matrix, we take the key vector K1 and value vector V1 and compute their rank 1 outer product. More specifically, the vector K1 transpose is a column vector of dimension dk by 1. The vector V1 is a row vector of dimension 1 by dv. The outer product between the two vectors is a matrix of size dk by dv. We update the state matrix by simply adding this outer product. For the following tokens, we repeat the same process. We take the key and value vectors, compute the rank 1 outer product, and use it to update the state matrix St. To compute a sequence of output vectors, we use the query vector and multiply it with the corresponding state matrix. The sequential computation reminds us recurrent neural networks. But in contrast to typical RNN that has vector size hidden states, here we have a matrix value hidden state. We call this a linear RNN. But why is this useful? In standard softmax attention, we need to cache all the previous key and value vectors in memory. This means that the memory requirements grow linearly with the sequence length. In contrast, in linear attention, we only need to store the state matrix St, which has dimension dk by dv. The memory requirement is constant, no matter how long the sequence is. This is great, but how do we train the linear attention model efficiently? There are three main challenges. First, as the figure shows, the recurrent structure means that we compute the output vectors sequentially. This sequential computation is inefficient and cannot leverage the parallel processing for training. Second, the computation of outer product involves only element-wise operations. Therefore, we cannot leverage the tensor cores in modern GPUs for efficient computation. Third, materializing the state matrix at every step leads to significant input-output overhead. How can we overcome these challenges? On the one hand, this is the recurrent form of linear attention. Alternatively, we can express the entire computation compactly using matrix multiplication in the fully parallel form. But the parallel form involves quadratic compute complexity with respect to the sequence length. The causal mask M prevents us from simplifying the computation by pre-multiplying the key and value matrices. To strike the balance between parallel and recurrent form, we have the Chunkwise parallel form. We first split the sequence into non-overlapping chunks of size C. Let's first see how we can compute the state matrix at the end of the first trunk without materializing the state matrix at every step. The state matrix S3 is the sum of the outer products of the key and value vectors in the first trunk. Due to the linearity property, we can express the sum of outer products as matrix multiplication. We form the key matrix K1 by stacking the transpose of the key vectors in the first trunk along the columns, and the value matrix V1 by stacking the value vectors in the first trunk along the rows. The state matrix at the end of the first trunk can then be computed using matrix multiplication. This matrix multiplication formulation facilitates efficient computation by leveraging tensor cores in GPUs. Furthermore, we do not need to materialize the state matrix at every step within the trunk. Now let's move on to the next trunk. Here we want to compute the state matrix at the end of the second trunk. From the state recurrence equation, we know that the state matrix S6 is the sum of the state matrix S3 and the key value outer products for tokens within the second trunk. Using a similar trick to express the sum of outer products as matrix multiplication, we can compactly express the state matrix S6 as the sum of S3 and the matrix multiplications of K2 transpose and V2. This gives us the following intertrunk recurrence relation. The state passing is still sequential, but the trunk level formulation greatly reduced the recurrent steps. For the output computation, we need to avoid materializing the state matrix at every step. Therefore, we decompose the output for each chunk into two parts. The first part accounts for the contribution from the hidden state from the previous chunk. This can be efficiently computed in parallel using the matrix multiplications of Q and S. The second part accounts for the contributions from the current trunk. Here, we leverage the parallel form for the output computation. With the sequential chunk level state passing and parallel output computation, Chunkwise parallel form interpolates between fully parallel and recurrent forms. Note that this formulation is mathematically equivalent and does not involve any approximation. The Chunkwise parallel form enables partially parallel, hardware-efficient training. It is now a standard recipe for training efficient linear sequence models. We can further improve the efficiency via IO-aware implementation like flash linear attention. But in practice, linear attention underperforms standard softmax attention on language modeling tasks. One potential reason is the lack of recency bias. This means that recent tokens should have more influence on the current token. But the additive nature of state metrics makes it challenging to capture recency bias. One approach to address this is to use a decay factor gamma, which acts as a gating mechanism to reduce and modulate the influence of earlier tokens. With the decay factor gamma, we can express the state recurrence equation like this. Here, the value of gamma is a constant between 0 and 1, specifying the decay rate. This is used in RedNet and lightning attention. But setting the right value of gamma is challenging and likely task-dependent. Therefore, we can introduce a data-dependent gating mechanism to dynamically adjust the decay rate according to the embedding vector. For example, the scalar gamma t can be computed by linearly projecting the embedding vector into a scalar value followed by a sigmoid function. Example models that use scalar data-dependent decay are Mamba2, MLSTM, and gated retention. But why restrict ourselves to using only scalar gating factor? For example, we can use a more expressive gating factor for fine-grained state memory control. However, introducing arbitrary matrix value gates greatly increase the training complexity and present additional efficiency challenges. Typically, we impose an outer product structure to ensure hardware-efficient training. This corresponds to a vector value gating vector alpha t. Such data-dependent multiplicative gates are used in gated linear attention, HGRN2, and RWKV6. With the outer product structures of the gating matrix, the formulation with expressive gating mechanism also supports efficient Chunkwise parallel training. But what does it actually mean to update the state matrix by adding the outer product of the key and value vectors? Let's take a step back and try to understand the update rule better. On the right-hand side, we have linear attention. On the left-hand side, we have the standard softmax attention. In standard softmax attention, we compute attention scores by taking the dot product of the query and key vectors and normalizing them with a softmax function. With key value caching, this implies that we have an explicit memory of all the key value associations. The stored key value pairs form an associative memory so that when given a new query vector, it can efficiently look up and retrieve relevant values based on the similarity between the query and the stored keys. This approach enables the model to flexibly adapt and learn from the given input context. But in linear attention, we do not explicitly memorize the key value pairs by storing them in memory. So how does linear attention manage to capture information from the historical context? One way to think about it is that it learns a regression function that maps the key vector to the value vectors. That is, using the key vector kj as input, we use this regression function to predict the value vector vj as output. In a sense, we encode the key value pairs from the context by compressing their information into our regression function. This can be regarded as the neural memory. In other words, we memorize the key value associations by making the value vector easily predictable from the key vector. But how do we actually train this regression function? We use the key and value vectors as our training data. For each key vector, we use the regression function f to predict the value vector. We can apply a loss function to the predicted value vector and the target value vector. More specifically, we aim to minimize the following objective function. Next, we need a method to learn the parameters of the regression function such that the predicted value vector closely match to the target value vector. We start with a linear regression function where the parameters are the weight matrix S. The output predicted value vector is a linear transformation of the input key vector. We use a simple loss function as a negative dot product between the predicted and the target value vectors. Here is a simple illustration. Suppose for a given token with the value vector v and key vector k, our goal is to find the weight matrix S so that the transform vector ks is close to the target value vector v. Now we need to design how we optimize the weight matrix S. A simple strategy is to use stochastic gradient descent. We consider one key value pair at a time and update the weight matrix S sequentially. At time step t, our loss is a negative dot product between the transform vector ks and the target value vector v. For each token, we can update the weight matrix by moving toward the negative gradient direction. Here, the beta t is the learning rate. This gives us the following update rule. Surprisingly, this update rule is exactly the same as the update rule for the state matrix in linear attention. This suggests that the state update in linear attention is equivalent to training a linear regression model with key value pairs using stochastic gradient descent. This has a deep connection with the fast wave programming concept, as it is updated rapidly and adapting to the changing input context at the task time. In contrast, the slow weights refers to the remaining model parameters that are updated slowly at the training time and fixed at the task time. But there's a problem. Training our regression function with this loss is not stable. For example, we can reduce the loss value by simply increasing the length of the transform key vector ks. An alternative is to use square arrow loss function. The loss at time t is thus the L2 norm of the difference vector between the predicted and the target value vectors. Similarly, we use the stochastic gradient descent to update the weight matrix S. Plugging in the loss function and computing the gradients, we get the following update rule. This update rule is known as the delta rule. The name delta emphasizes the incremental correction driven by the arrow between the target and the predicted value vectors. The delta update rule represents gradient descent on square arrow loss, but it was used even before the concept of gradient descent was established. Now let's visualize and understand how delta update rule works. The first step is to retrieve the predicted value vector using the current key vector and the previous state matrix as t-1. This is the predicted value vector VO before we update the state matrix. Next, we compute the data-dependent weight beta t using the embedding vector. The beta t controls the writing strength of the current value vector vt. We then use this weight to linearly combine the current and the old value vectors. This results in a new value vector vnew. The delta rule updates the state matrix by erasing all value associated with the current key vector and adding new values into the memory. These two update equations are exactly the same. However, it provides a clear intuition of how delta rule dynamically remove and add key value associations. In contrast, linear attention updates the state matrix by blindly accumulating the outer product of the key and value vectors, without a mechanism to remove stale associations. But how can we train this model at scale? A naive approach will involve a sequential algorithm, which cannot be parallelized across the sequence length. To do so, we need to formulate the Chunkwise parallel form for hardware-efficient training. Let's first do a quick recap of Chunkwise parallel form for linear attention. After splitting the sequence into non-overlapping chunks of size C, we compute the state matrix at the end of each chunk using matrix multiplication. This allows us to compute the state matrix efficiently by leveraging tensor cores and avoid materializing the state matrix at every step. The output vectors are then computed in a parallel manner by summing the contributions from the previous chunk and the current chunk. Now let's see how we can do the same for delta update rule. Let's begin by expressing the delta update rule as a recurrence relation. By grouping terms involving the previous state matrix, we get a clean recurrence relation. To simplify the notations, we label these matrices as AT and BT. Now let's unroll the recurrence to see how it works step by step. The state matrix after the first token is A1 times S0 plus B1. But since the initial state matrix is all 0, the state S1 is simply B1. Let's look at the second state matrix S2. Here we unroll the recurrence by replacing S1 with B1. This gives us the state matrix S2 as A2 times B1 plus B2. Now the third state matrix S3. Following the procedure, we unroll the recurrence by replacing S2. Similarly, we unroll the recurrence for S4. By now we can see a clear pattern. The state matrix ST is the sum of the matrix B1, B2 to BT, each multiplied by the corresponding matrices. As a result, we can express the state matrix ST as the sum of the matrices BI with the multiplication of AT, AT-1 to AI plus 1. We can further simplify the expression into a more compact and more scary form. This is nice. But what we really care about is establishing the chunk-level recurrence relation. Since the matrix ST consists of T terms, we can decompose them into two parts. The first part consists of terms from the first chunk. The second part consists of the remaining terms from C plus 1 to T. Similarly, the multiplications of the matrix AJ for J from I plus 1 to T can be decomposed into two parts as well. This part corresponds to C plus 1 to T, and this part corresponds to the term from the first chunk. We see that this term does not depend on the index I, and therefore can be factored out from the summation. Now let's pay attention to this part. It has exactly the same form as the state matrix ST, but with the summation up to C. This is the state matrix at the end of the first chunk. We denote this state matrix as S1. This gives us the chunk-level recurrence relation. It illustrates the current state matrix ST consists of the state from the previous chunk propagated up to the time t, and the new contributions coming from the current chunk. Here is the general formula for the chunk-level recurrence relation. We denote the SRT as the state at R step within the T's chunk. Now the key challenge is to formulate these two parts as matrix multiplications to enable hardware-efficient training. The product of multiple matrices, in general, cannot be computed efficiently. But the matrices here have special diagonal plus low-rank structures. Leveraging these special structures, we express the product of matrices as the identity matrix minus the sum of rank 1 outer products. As we showed earlier, these can be computed efficiently using matrix multiplications in a parallel manner. The key trick enables this is applying the WY representation proposed 40 years ago. However, computing the vectors W and U remains challenging due to their recursive formulation. Luckily, these recursive updates can be rewritten in matrix form by applying the UT transform. With these derivations, we can now express the chunk-level recurrence relation in matrix form. The output can also be computed efficiently in parallel. This is great, but delta update rule has a limitation. It updates just one key value association per time step, using only the current key value pair for its gradient update. For state matrix dk by dv, the forgetting speed is slow since it will take dk step to fully erase the memory. To address this, we can leverage the gating mechanism to control the forgetting speed dynamically. For example, the scalar value forget gate used in gated DeltaNet. We can further use a more expressive value vector forget gate to dynamically control the forgetting speed for different feature dimensions. This has been explored recently in Kimi delta attention. But the delta update rule only updates one key value association per time step, effectively running SGD with the most recent training example. Let's explore how we might improve from the perspective of optimizing a test time objective function. One idea is to extend DeltaNet by taking multiple gradient steps for each time step. This approach is known as delta product. Delta product produces more expressive state transition matrices, diagonal plus low rank, and shows better performance than DeltaNet in state tracking, length extrapolation, and language modeling. Instead of updating one key value pair per step using recursive designs, Longhorn derives a closed-form update rule from online learning objectives. But both DeltaNet and Longhorn focus exclusively on the prediction error of the current token. MetaLayer, in contrast, consider the prediction errors across all previous tokens. It is later extended to MetaNet to enable chunkwise parallel training. Besides optimization, the form of the regression function is also very important. At its core, we are training a regression function at a test time that forms key value associations, enabling effective in-context learning. So far, we have only considered a simple linear regression function. But can we use a more expressive mapping? In linear regression, a simple method to enhance the model's ability to capture nonlinear relationships is to apply a nonlinear feature transformations to the input data. For example, here we want to feed a 1D function to these data points. A linear model based on the input x will only feed a straight line, which is not able to capture the nonlinear relationship. Instead, we can include polynomial terms to the input features. This allows the model to capture the nonlinear relationship while still being linear in its coefficient. But the key question is what type of nonlinear feature transformation can we use? Once we transform the input query, key, and value vectors with a kernel feature function phi, we can apply a linear regression function as is. One of the earlier attempts is to use this function to approximate the exponential kernel used in Softmax attention. Several other mappings are also explored, such as random feature maps, positive orthogonal random features, and so on. Here are some more examples. But instead of using a fixed manually designed feature transformation, can we learn this transformation from data? This leads to the line of work of test time training, TTT. To further improve the performance, we can include momentum and weight decay for optimizing the regressions as the neural memory module. This gives us the method of Titan. However, test time training models face challenges when dealing with long context data, primarily because small online mini-batch sizes limits the effectiveness of fast weight updates. This limitation can be alleviated with large chunk test time training, where fast weights are updated using much larger chunks of data. This approach greatly enhances the long context modeling capability. Rather than designing increasingly complex architecture for long context modeling, recent work on test time training focuses on continual learning from context. Specifically, we update a subset of parameters in a transformer at test time using next token prediction. This end-to-end approach offers promising results. It matches the scaling of full attention transformers with respect to context length, while offering constant inference latency. These developments mark a new frontier in sequence modeling design, enabling efficient, long-context processing without the computation and memory constraint of standard Softmax attention. I hope you enjoyed this overview. Thanks for watching, and I'll see you next time.